Good morning, my YouTube viewers. This is Crystal, and in this video, what I'm going to be talking about is 3 issues about sampling distributions. So the first thing we're going to talk about is a sampling distribution. So a sampling distribution is the probability distribution of a given statistic based on a random sample. And then so what we're going to do is we're going to go over the code of our programming to demonstrate a sampling distribution of the sample mean. So the first thing we're going to do is we're going to create the population from the sample mean. So we're going to set our seed, and that's set.seed brackets 1, 2, 3. And so basically every time you run the cell or run the program, it will initialize the variables to the same value, and that's why you want to set your seed. And now what we're going to do is we're going to create our population. So population becomes our norm, brackets, 100,000, mean equals 50, SD equals 10. So our norm means a randomly sampled normal distribution. That's what R naught means. 100,000 means it's 100,000 elements in that sample. You've got a mean of 50 and a standard deviation of 10. And so now we're going to set the parameters for the simulation. So N becomes 30, which is your sample size. Num samples becomes 1,000. So it means that you're going to take 1,000 repeated samples. You're going to store the means somewhere. So sample means becomes numeric num samples. So you're going to have a numeric variable with 1,000 elements in it. So that's sort of going to be like a empty list in Python. And the reason why is because we're going to store the elements in this numeric value called sample means. So in Python, it would just be an empty list, but in R, you call it numeric bracket num samples. And the number of elements in it is going to be the num samples, which is 1,000. So you're going to draw the repeated samples and compute the means. We have a for loop for I in 1 to num samples. Sample means I becomes mean bracket sample population in comma replace equals true. So that's the mean of the sample of the population, which is going to have 30 elements in it, and you're going to replace every element after you have sampled it. So you're going to have sample with replacement. So now what we're going to do is we're going to calculate the true population mean. True mean becomes mean of the population. And then we're going to plot the sampling distribution. So we're going to plot the sampling distribution by creating a histogram. So hist becomes sample means. So sample means is like a list or an array or a vector, and it's got 1,000 elements in it. And then so what you've done is you have sampled your random distribution 1,000 times. And every time you have sampled the random distribution, what you've done is you've taken the mean of that sample and you've put it into sample means. And so you have done that 1,000 times. And the reason why is because the num samples is 1,000. So you've got your true mean, which is the mean of the population, and then you've got your sample means, And sample means I is position in the vector. The position in the vector where the sample means are placed. So we're going to create this histogram. Hist bracket sample means, so that means it's going to have 1,000 elements in it. Breaks equals 30, color equals light blue, border equals white. Main, that's your title. Sampling distribution of the sample mean. X lab, that's the label on your x-axis, is your sample mean. We're going to put a vertical line to annotate the true population mean. AB line, brackets, V equals true mean, comma, color equals red, comma, line width equals 3. And we're going to put a vertical line for the mean of the sample means. So AB line, brackets, V equals mean, brackets, sample mean. So that's the mean of the 1,000 sample means that you took. And color equals dark green, line length equals 3, LTY equals 2, and then we're going to put a legend there. So legend means we're going to create a vector. So your paste is like a print command, but you use paste when you want to use text and the values. So paste true mean is the true mean, and paste mean of sample means is the mean, round mean of sample means. Color is going to be a vector of red and green, so your true mean is red, and your mean of sample means is dark green. Line width is 3, LTY is another vector, bracket C, comma, 1 and 2. So 1 is going to be a straight line, and 2 is going to be a dashed line, and BTY equals N. So we create a histogram, and you can see that this is a histogram, and so this is a sampling mean of the sample distribution. So you can see that the true mean is 50.01, and the mean of the sample means is 49.99, which is very close to the true mean. And it's also good to know, because your true mean is a straight line and your sample mean is a dashed line, then you're able to see that the sample mean is, you can see both the true mean and the sample mean with the true, with the straight line and the dashed line. So now what we're going to talk about is the central limit theorem. So what the central limit theorem is that it doesn't matter what your distribution is. It can be any distribution. But if you continuously sample that distribution, then the means of those samples are going to form a normal distribution. And so that's basically what the central limit theorem is. And so what we're going to do is we've created a program so we can demonstrate the simple central limit theorem. So the first thing that you want to do is you want to set the seed. And the reason why you set the seed is so every time you run the program, it will initialize the variables to the same values. So set.seed brackets 1, 2, 3. And then we're going to create a highly skewed population. We're going to have an exponential distribution. So population becomes REXP brackets 100,000, comma, rate equals 1 over 10. So R means randomly sampled, and EXP means an exponential distribution. It's going to be sampled. It's going to have 100,000 elements in it, and the mean is going to be right skewed. So we're going to simulate the settings. So our number of samples is going to becomes 2,000, and the sample size becomes 30. And so now we're going to create a variable to actually store our sample means. So sample means becomes numeric bracket num samples. So that's kind of like an empty array but it's only as long as the num samples, and the num samples is 2,000. And then we're going to draw repeated samples and compute the sample means. So we're going to create a for loop to do that. For I in 1 num samples, sample means I, and I is the placement in the vector of that element. Becomes mean, brackets sample, brackets population, comma n, comma replace equals 2. So you're going to take the mean of the samples of the population, and the sample size is going to be 30. No, the sample size is going to be 2,000. And n is going to be 30. Sorry, I got that wrong. Your sample size is going to be 30. And population is going to be 100,000. And you're going to sample with replace. So that means every time you sample something, you put it back into the population after you've sampled it. And so now we're going to plot a sampling distribution. We're going to create a histogram. So hist bracket sample means, and that's going to be 2,000. I believe it's 2,000 if we come back up to here. Sample means is 2,000. So it's going to be a list or an array or a vector with 2,000 elements in it. Breaks equals 30. Color equals light blue. Border equals white. Main is your title, which is central limit theorem, sampling distribution of the mean. The X lab is the label on the X axis is the sample mean. So we're going to add the true population mean. True mean becomes the mean of the population. And then we're going to add a vertical line to illustrate the true population mean. So AB line brackets V equals true mean, color equals red, line width equals 3. And then we're going to add the mean of the sample means. So AB line brackets V equals mean sample means. And so basically you're taking that array or list or vector of sample means, and you're going to take the mean of that, which is, I think, 2,000. Color equals dark green. Line width equals 3. LTY equals 2. And then we're going to put a legend in there. Legend, we're going to create a vector. So you're going to paste the true mean, the round of the true mean, and then you're going to paste the round of the sample mean. And the color, you're going to create a vector. So the true mean is red, and the dark green is, the mean of the sample means is dark green. Line width is 3. LTY, that's going to tell you whether it's straight or dashed. So the is C brackets 1, comma 2. So the true mean is straight, and the mean of the sample means is 2, and BTY equals N. So we've created this histogram, and basically you can see the histogram is still a little bit skewed to the right because we use the exponential distribution to actually take the samples. But you can see that it has approaching a normal distribution. So your mean is 9.97, and your mean of the sample means is 10. And then so if you had increased the number of samples, because you had 2,000 samples, if you had increased the number of samples to say 5,000, then the distribution that the means would create would more closely resemble a normal distribution, because the more times you sample this exponential distribution, the means of the samples will begin to look like a normal distribution. So the next thing we're going to talk about is confidence intervals. And confidence intervals is something that you're going to need to become familiar with. So confidence intervals are derived using the probability theory. For example, a 95% confidence interval for the population mean is constructed so that 95% of all such intervals calculated from random samples will contain the true population mean. And so what we've done is we are creating a program to demonstrate to you how confidence intervals work. So we're going to generate the sample data. The reason, and then we're going to set the seed, is set.seed brackets 1, 2, 3. And the reason why we set the seed is so every time you run the program, the variables will initialize to the same values. So we're going to create our sample data. X becomes our norm, brackets 50, comma, mean equals 10, comma, ST equals 2. So that means you have a normal distribution that is randomly sampled. And this normal distribution has 50 elements in it with a mean of 10 and a standard deviation of 2. So now we're going to create the point estimate, which is the sample mean. So point S becomes mean of X. So that's the mean of your distribution. Now we're going to create a standard error. Standard error becomes SDX divided by the square root of length of X. So SD is your standard distribution, standard deviation of X divided by the square root of length of X. So length of X is 50, so it's going to be the square root of 50. So it'll be a little over 7. So because 7 times 7 is 49. So it'll be a little over 7 is the square root of 50. And now we're going to determine our confidence interval using a G-distribution. So alpha is 0.05. Alpha is also quite often called your confidence level. T crit becomes QT brackets 1 minus alpha divided by 2, comma, DF equals length of X minus 1. So 1 minus alpha, that's 1 minus 0.05 divided by 2, and your degree of freedom equals the length of X minus 1, so that's going to be 49. So your lower confidence interval becomes point estimate minus T crit times SE. So it's going to be the point estimate minus your critical level times a standard error. And your upper confidence interval becomes point estimate plus T crit times SE. And then that is that's going to be your point estimate plus the critical value times standard error. So now we're going to plot all of these values onto a histogram. So with the CI, that's confidence interval lines. So you've got hist brackets X, and X is your population distribution. Main equals histogram with mean and 95% confidence intervals. X lab is your label on your x-axis being value. Color equals light blue. Border equals white. And then you're going to put a line of the mean there. So AB line brackets V equals point estimate. Color equals red. Line width equals 3. And then you're going to put your confidence interval lines. So AB line brackets V equals lower, comma, color equals dark green, comma, line width equals 3, comma, LTY equals 2. Then you have AB line brackets V equals upper, comma, color equals dark green, line width equals 3, LTY equals 2. And then we're going to create a legend. So the legend is going to be on the top right, and then you're going to create a vector that's got paste is your mean and the rounded mean. Paste is your lower confidence interval, and that's rounded. and paste is your upper confidence interval, and that's rounded. Color is going to be red for your mean and dark green for your lower and your upper confidence interval. Line length equals 3. Okay, LTY, you're going to create another vector, C brackets 1, 2, 2. So 1 means it's a straight line, and 2 means it's a dashed line, and BTY equals N. So we have created a histogram with the population and the mean and the lower and the upper confidence interval. So your mean is 10.07, your lower 95%, your lower confidence interval is 9.54, and your upper 95% or your upper confidence interval is 10.6. So that means that the value should fall, well, 95% of the values should fall between 9.54 and 10.6. So that concludes this video. The next video is going to be another topic on estimation. And so I hope you decide to watch it. And thank you for watching this video.